Hey everyone, really glad you're here. So, for today's explainer, we've got a very specific, honestly pretty exciting goal. We are going to completely demystify the internal architecture of Argo CD. We're going to crack it open, look at the gears turning inside, and figure out the core microservices that make this incredible GitOps engine tick. Let's just dive right into it. Okay, picture this absolute nightmare. It's 4 p.m. on a Friday, production is suddenly breaking, and you realize someone updated a node configuration on your Kubernetes cluster. Maybe they added a taint or messed with resource limits. You frantically ask the team, who made that change? And crickets. You see, in traditional setups, there's just zero mechanism to track that. No versioning, no real auditing. You might know someone logged in, but you have no clue what they actually tweaked. It's basically absolute chaos.
So here's our roadmap for this explainer. We'll start with the chaos before GitOps, then look at the GitOps solution itself. From there, we'll do a high-level view of Argo CD, peek inside at the core microservices, talk about access, identity, and memory, and finally wrap up with the magic of reconciliation.
All right, part one, the chaos before GitOps and those dreaded untracked changes.
To really frame the problem we're trying to solve here, let's compare the old way with the new way. For years, right, we've had amazing CI, continuous integration for our source code. You submit a PR, it gets reviewed, versioned, and merged. Beautiful. But the CD part, continuous delivery, man, especially for infrastructure, we were stuck in the dark ages. We're talking shell scripts, random Python scripts, or literally just someone manually running kube control commands. No versioning whatsoever. GitOps steps in and essentially asks, hey, if our source code has a trackable, reviewed process, why shouldn't our infrastructure? Which brings us to part two, the GitOps solution, and honestly, a total paradigm shift. It is officially time to stop manually tweaking servers. We need to start treating infrastructure exactly like application code. The fundamental philosophy here is simple, but it's incredibly powerful. Git becomes your absolute single source of truth. And I really want to emphasize this. It's not just for delivering your apps. A huge percentage of users rely on GitOps entirely for managing infrastructure. I mean, think about it. When you're dealing with hundreds of Kubernetes clusters, which is literally thousands upon thousands of resources, managing all that infrastructure actually gets way more complex than just pushing a few app updates.
So the real superpower GitOps gives you is this thing called continuous reconciliation. This is the North Star of GitOps. It basically means the system is always watching. If someone, whether it's a well-meaning dev or worse, a malicious hacker, goes directly into the cluster and makes a manual change, the GitOps controller steps in and says, yeah, absolutely not. It instantly sees that the live cluster doesn't match the Git repo, and it automatically overrides the manual change, healing the cluster right back to the desired state. Honestly, it's a massive security advantage.
Moving into part three, Argo CD, the high-level view of this GitOps engine. So, who exactly is the enforcer making all this auto-healing happen? Well, consider this. It has over 13,000 GitHub stars. Argo CD is wildly popular. It was originally built by engineers at Applitix, which got scooped up by Intuit, and today it's a fully graduated project over at the Cloud Native Computing Foundation. It's got heavy-hitting contributors from places like BlackRock, Red Hat, and CodeFresh. It is, without a doubt, an absolute powerhouse in the Kubernetes ecosystem. At a really high level, you can just think of Argo CD as a highly specialized Kubernetes controller. It acts as the ultimate bridge. On one side, you've got your Git repo holding all your declarative YAML manifests. On the other side, you have your live breathing Kubernetes cluster. Argo CD just sits right there in the middle, continuously syncing the two. But, saying it bridges the gap is the easy part. How does it actually pull that off under the hood? Let's find out in part four, inside Argo CD core microservices. Okay, time to peel back the curtain. I want you to think of Argo CD not as one big monolithic program, but more like a team of specialized workers. Each one is hired to solve a very specific piece of the puzzle. There are three primary microservices running the show. The repo server talks to Git, the app controller talks to Kubernetes, and the API server talks to, well, you, the user. Let's break down what each of these workers is actually doing day to day. First up on the roster is the repo server. Honestly, you can sort of personify this one as a hyper-focused, dedicated researcher. Its entire job in life is just to connect to your version control system, which is almost always Git, and constantly pull down the desired state. It fetches those declarative YAML manifests you've committed and holds on to a cached understanding of exactly what the infrastructure should look like. Next up, the application controller. So if the repo server is the quiet researcher, the application controller is the muscle. It's the enforcer. This is actually a stateful microservice that connects directly to your Kubernetes cluster to figure out the actual live state of what's running right now. Then it talks to the repo server, gets that desired state we just talked about, and compares the two. If there's a mismatch, the application controller steps up and enforces the truth defined in Git by applying the right manifest straight to the cluster.
Part 5. Access, Identity, and Memory. Meet the supporting cast.
Now, those two main components are great, but they can't do it all alone. If you're a developer or a DevOps engineer, you actually need a way to interact with this whole system, right? You want a web dashboard, or maybe you prefer the command line interface. And that is exactly where the API server comes in. It acts as the front door, the primary gate for all user interactions. It takes your commands and securely routes them right into the ArgoCD backend. What's really slick, though, is how ArgoCD handles the bouncer duties for that front door. Out of the box, it comes bundled with a component called Dex. Dex is basically this brilliantly lightweight OIDC proxy. So instead of forcing you to create and manage totally new usernames and passwords just for ArgoCD, Dex instantly hooks into your company's existing identity providers. Whether your team uses Gmail, an internal LD app database, or Facebook, Dex seamlessly layers single sign-on right onto the API server.
And rounding out our tour of the internal architecture, we have Redis. Now, remember earlier when I mentioned the application controller is stateful? It is keeping track of a massive, and I mean massive, amount of cluster data. If the application controller pod crashes or just goes offline for whatever reason, it needs to recover instantly without having to sluggishly rescan the entire cluster from scratch. So Redis steps in as the high-speed system memory. It caches all that critical cluster info so ArgoCD stays incredibly fast and super resilient. Finally, part 6, the magic of reconciliation. Let's see this auto-healing in action. All right, let's bring all these microservices together. The really crucial takeaway here is how this continuous loop operates in real time. Step 1, the repo server caches your latest Git commit. Step 2, the application controller is constantly pulling the live state from Kubernetes, leaning on Redis to cache it. Step 3, the application controller checks the math. It detects a difference. Say someone hopped in and manually tweaked a node configuration. It instantly leaps into action, overriding that manual change and syncing the cluster right back to the exact state the repo server fetched in step 1. Boom. That is the true magic of continuous auto-healing in GitOps. But before we wrap up this explainer, I want to leave you with a pretty fascinating edge case to chew on. We keep saying Git is the absolute single source of truth, right? But what if you have a Kubernetes admission controller? You know, the kind that automatically injects mandatory resource limits or security labels onto your pods the exact second they're deployed. Obviously, those labels aren't in your Git YAML, so will ArgoCD see those injected labels, assume the cluster's out of sync, and just constantly try to delete them in a never-ending loop of failed deployments? Like, how does a strict GitOps engine handle dynamic cluster mutations that happen outside of Git? It's a complex little nuance of ArgoCD's architecture, and it'll definitely make you rethink how strict your single source of truth really is. Definitely keep that in mind as you continue your GitOps journey. Thanks so much for hanging out and learning with me today, and I'll catch you in the next explainer. Welcome to this explainer. So today we're diving into a massive, frankly critical, mechanical shift in how we actually handle deployments. Look, if you've been working with software infrastructure lately, you already know the old ways of getting code from a developer's laptop out into production are changing fast. We're moving towards this practice called GitOps, and this evolution, going from a traditional push-based deployment to a pull-based model, it's literally reshaping how we manage infrastructure from the ground up. And honestly, it is absolutely vital right now, especially for fast-moving AI systems where model versions and configurations are just constantly, endlessly being updated. Because here's the core problem we're all facing right now. Think about it. How do you actually keep your deployments consistent when your systems are changing continuously? Imagine you're working with agentic or AI systems. Your team is probably tweaking model versions, adjusting inference services, updating prompts, maybe modifying embedding pipelines, all at breakneck speed. With all these rapid-fire changes happening all at once, how do you keep it together? How do you maintain accountability so you know exactly who changed what and exactly when they did it? You absolutely need structure. You need a highly auditable system to stop everything from just evolving into total chaos. And while the solution to that chaos is GitOps. Simply put, GitOps is all about using Git, the exact same version control system you already use for your code, but using it as the single, definitive source of truth for your applications in your infrastructure. So instead of someone saying, oh, hey, I deployed this manually to the server, GitOps lays down the law.
Whatever is stored in Git dictates exactly what your cluster must look like, period. Your Kubernetes manifests, your Helm values, environment variables, app versions, the whole shebang. They all live centrally right there in Git. It basically becomes your ultimate control center. Now, to truly get why GitOps is such a game changer, we kind of need to look at the pure mechanical differences compared to what we've been doing for years. Let's walk through the traditional CI/CD flow, right? The classic push-based deployment. Okay, step 1. A developer pushes code. Easy. Step 2, a continuous integration pipeline kicks in, installs dependencies, builds a container image, and scans it for vulnerabilities. So far, so good. But then we hit step 3. That pipeline takes your shiny new image and literally pushes it directly into the cluster to deploy the changes. The pipeline reaches from the outside straight into your production environment. And you know, what's really interesting here, and honestly kind of terrifying when you think about it, is the massive inherent risk of that direct connection. Because that CI pipeline is pushing changes directly into production, the CI/CD system itself has to hold the credentials to your cluster. It needs the keys to the kingdom. If that push pipeline gets misconfigured or, heaven forbid, compromised by a bad actor, that attacker now has a direct, wide-open, vulnerable line straight into your live production systems. Plus, think about this. If someone just bypasses the pipeline entirely and tweaks the cluster directly, there's zero record of it. Poof, nobody knows who did what. Enter the GitOps pull model. Now, this builds on those first couple of steps, but it completely flips the deployment mechanics on its head. Step 1 is exactly the same. The developer pushes code. The CI pipeline still does its thing, it builds and scans the image, but right here is the absolutely crucial mechanical shift. The pipeline stops. Full stop. It does not touch the cluster. Instead, for step 2, the pipeline simply updates a totally separate configuration repository with the new desired state. And then, for step 3, a controller that actually lives entirely inside your cluster detects that change, reaches out, and pulls the new desired state in. Boom. We have effectively entirely decoupled continuous integration from continuous deployment. To really lock this concept in, let's personify these two models for a second. Let's call it the deployment mindset matchup. The traditional push model, it basically has the attitude of, okay, I finished building, so now I'm going to connect to the external cluster and force my deployment onto it, right? It's an external entity imposing its will. The pull model, though, is more like an internal worker saying, hey, I live inside the cluster. I'm just quietly over here watching Git. If anything changes over there, I'll fetch it and update myself to match. It's night and day. One forces changes from the outside, the other fetches them safely from the inside. So why does this specific mechanical difference matter so much? Well, the security and reliability advantages are just massive. First off, your cluster never exposes its deployment access credentials to external CI systems ever again. That makes it infinitely more secure. Second, because Git is the absolute, unquestioned desired state, the system automatically detects if the actual state in your cluster starts drifting from what's in Git. Third, you get a pristine, full audit trail. Every single change is a Git commit, even if it was co-authored by an AI coding tool. And finally, the ultimate safety net. If your entire cluster just spontaneously dies, you can rebuild the whole thing from scratch, directly from Git, because the entire blueprint is safely stored right there. Section 1. GitOps operators, ArgoCD and FluxCD. So let's talk tools. Both ArgoCD and FluxCD are Kubernetes native, and they both follow that exact same core philosophy: watch Git and reconcile the cluster. But they definitely have different flavors. ArgoCD focuses heavily on visibility and control. It gives you this really robust built-in user interface so you can easily visualize your application state. FluxCD, on the flip side, really leans hard into modularity, automation, and self-healing. By default, Flux actually has no UI at all. It relies on a set of separate, highly specialized controllers, like a source controller, a Helm controller, and each one just does its one specific job exceptionally well. Choosing between them really just comes down to what your specific infrastructure team values most. Section 2. Real-world GitOps scenarios, putting theory into practice. Okay, picture this. It's a classic nightmare scenario. It's 2 a.m., an engineer is frantically trying to patch a live bug, and out of sheer desperation, they completely bypass the pipeline. They just manually edit a Kubernetes deployment directly in the cluster using a basic command line edit. Now, under a traditional push model, that rogue change, it just sits there, totally undocumented like a ticking time bomb, waiting to cause massive confusion down the road. But in GitOps, what happens? Drift detected. And honestly, this is where the absolute magic happens. ArgoCD or FluxCD will instantly realize that the actual state of the cluster no longer matches the desired state stored in Git.
If you have self-healing enabled, the controller will automatically overwrite that manual rogue change and restore the deployment exactly back to the Git-defined state, period. Git is the boss. It enforces that consistency continuously, no matter what happens at 2 a.m.
Let's look at another super high-stress scenario. Imagine a new release goes out and production immediately breaks. Users are getting errors, alarms are ringing everywhere. In a traditional setup, fixing this is a nightmare. It might involve hunting down an older artifact, kicking off a wildly stressful pipeline rebuild, and just praying to the deployment gods that it pushes correctly. But how do we fix this exact same problem the GitOps way? You just revert the Git commit. Seriously, that's it. Rolling back a totally broken production environment becomes a trivial, everyday version control operation. You just revert the exact commit that introduced the bad state, Git goes back to the previous known good state, and that trusty controller inside the cluster immediately pulls that updated, safe configuration. The panic is completely gone and it's replaced by calm, predictable mechanics.
All right, so let's quickly test your understanding of this newly decoupled architecture with one final scenario. Let's say your CI tool, maybe GitHub Actions, has successfully built a shiny, brand new container image. Should that CI system now take that image and deploy it directly to the Kubernetes cluster? The answer is a big, resounding no. And this is the strict, fundamental mechanical boundary of GitOps. GitHub Actions should only ever update the configuration repository on Git. Its job completely ends right there. The GitOps controller, sitting safely and securely inside the cluster, takes over from that exact point. It sees the update waiting in Git, and it pulls the deployment in itself.
Which really brings us to the ultimate takeaway of this whole explainer. This evolution from push to pull, it isn't just some slight process tweak or a new buzzword. It is a fundamental shift in how we secure and maintain the actual, literal mechanics of deployment. So, as you look at your own infrastructure today, I want to leave you with this one thought. Does your current deployment pipeline still have a direct, vulnerable line straight into production, or are you finally ready to let the cluster pull the strings?
All right, let's jump right into it. Today, we're breaking down the philosophy of GitOps, and specifically why modern, cloud-native infrastructure relies almost entirely on what we call declarative logic. Look, if you've ever felt like managing infrastructure is just a constant battle of micromanaging, putting out fires, and running endless manual commands at 2 in the morning, you're definitely in the right place. We're going to completely flip that paradigm in this explainer and show you how to automate your environment using the exact same tools your devs are already using. So, here's our game plan for today. We'll cover imperative versus declarative logic, the evolution to GitOps, push versus pull deployments, ArgoCD, the thermostat, managing state and syncing, and finally, guardrails for GitOps.
Okay, starting off with Section 1, imperative versus declarative logic.
The absolutely crucial point here is understanding how we actually communicate with our systems. Imperative logic, that's micromanagement. That's you at a terminal typing out explicit commands step by step. You say, create exactly 5 pods, then create this service, then open this port. You're doing all the heavy lifting. Declarative logic, on the other hand, just hands over a blueprint. You give the system a configuration file and basically say, hey, just make it look like this. And the system completely figures out the steps to get there.
Instead of these massive, fragile scripts filled with manual commands, you're using declarative YAML files. You define your exact needs, how much RAM, CPU, node count, which container images to pull. You bundle all of that up, hand it over to Kubernetes, and Kubernetes just takes care of the rest. You're declaring the final destination, not charting out every single turn on the path to get there.
Moving on to Section 2, the evolution to GitOps.
To really grasp GitOps, we need a quick refresher on standard pipeline evolution. First up is continuous integration, or CI. This is the starting line. When a developer finishes a feature, they merge their code into the main branch. The system kicks in, creates a build, runs the tests, and basically makes sure the new code hasn't blown anything up.
Next, we have continuous delivery. This takes CI and extends it by automating the release cycle. So your code is built, it's tested, and it's totally prepped for release. But usually, in continuous delivery, actually pushing that code live still requires a human being to literally press a button.
Building on that, we hit continuous deployment, and this removes the human button click entirely. Once those changes are validated and greenlit by the tests, they go straight out to production automatically. No manual intervention, just a smooth, continuous pipeline from the developer's laptop right to the live server.
Which brings us beautifully to GitOps.
GitOps takes that continuous deployment concept for cloud-native apps and marries it directly to declarative logic. It establishes your Git repository as your single source of truth. If you want to change your live cluster, actually, scratch that. You don't even touch the live cluster anymore. You update your declarative YAML files in Git, and the automation takes over to make reality match your repository. You can finally say goodbye to the sheer terror of manually SSHing into a live production cluster to fix a typo.
All right, Section 3. Push versus pull deployments.
Traditionally, CI/CD pipelines used a push approach. A pipeline finishes a build and then forces those changes directly into production. But think about what that actually requires for a second. It means giving your external deployment pipeline God mode access to your infrastructure. That is terrifying. GitOps completely flips the security risk on its head by using a pull-based deployment instead.
In a pull-based setup, the communication flows the opposite way. You update your configuration in Git. Then your actual live environment continuously checks that repository, basically tapping it on the shoulder asking, "Hey, do you have a new version for me?" If there's an update, the environment reaches out, pulls the new state down, and applies it internally.
The reason this is such a game changer is entirely about security. By keeping the deployment logic locked inside the cluster, your external pipelines do not need administrative credentials to your production environment. You are eliminating a massive vulnerability right out of the gate. This fundamentally flips the security paradigm, making the pull-based approach the absolute gold standard for GitOps today.
Let's dive into Section 4, ArgoCD, the thermostat. So you might be wondering, how does a cluster just know how to continuously monitor a Git repo and pull these changes? Well, the magic happens through Kubernetes controllers, and specifically, a brilliant tool called ArgoCD.
To really wrap your head around ArgoCD, think about the thermostat in your house. It's honestly the perfect real-world analogy for declarative logic. You don't tell the heater exactly how hard to work or when to spin its fan. You just declare a desired state, let's say 25 degrees. If the room is currently 21 degrees, the thermostat detects that discrepancy and kicks on the heat until reality perfectly matches what you asked for. ArgoCD does exactly that, but for your infrastructure. It's a controller living right inside your cluster, constantly monitoring your running applications. It looks at their live state, looks back at the declarative YAML files sitting in your Git repository, and continuously asks, does reality match the blueprint?
Section 5, Managing State and Syncing.
Let's quickly map out the core vocabulary here. The target state is what you want. That lives safely in your Git repository. The live state is what's actually running right now in your Kubernetes cluster. And the sync status is basically ArgoCD's report card telling you if those two things perfectly align.
If they don't align, you get flagged as out of sync. Now, this obviously happens when you merge a new update into Git, pushing the target state forward. But what's really cool is it also happens if someone goes rogue and manually tweaks a setting directly in the live cluster. ArgoCD immediately notices, flags it as out of sync, and works automatically to overwrite that manual change, pulling things right back into alignment with Git. It's essentially self-healing infrastructure.
And our final section, number 6, Guardrails for GitOps.
Because ArgoCD blindly trusts whatever blueprint is sitting in your Git repository, you absolutely need tools like Daytree to act as guardrails. Daytree runs right in your CI pipeline, validating your YAML files before they are ever allowed to merge. For example, ArgoCD needs specific labels, like part of ArgoCD, just to recognize resources like config maps. Daytree checks for those labels automatically. If they're missing, it fails the build right there, stopping a misconfiguration dead in its tracks.
You have to remember, because this whole system relies entirely on declarative logic, literally one typo in a config file can break your deployment loop. Powerful automation demands powerful validation. It's like the thermostat analogy again. If you feed a broken temperature sensor into the thermostat, the whole house is going to freeze.
As we wrap up this explainer, I want you to take a hard look at your own systems. Ask yourself, is your infrastructure resilient enough to fix itself using declarative blueprints, or are you still out there micromanaging every single deployment with imperative commands? By making the shift to GitOps, you aren't just speeding up your deployments, you are creating a highly secure, self-healing environment where your code repository truly is the one and only source of truth. Thanks for hanging out with me for this one, and I'll catch you next time.